Hypothesis test for a regression coefficient. Let's look at an example. Suppose the analyst wants to find the relationship between the returns on stock D and the market. Therefore, using monthly returns over the last 5 years, which works out to 60 observations, the regression model produces the following results. So I'm just going to jump a little bit ahead here, and this is what the regression model looks like, right? We have the dependent variable, and we have some constant plus the beta coefficient, which measures how sensitive the dependent variable is on the independent variable. So when we talk about the coefficients, we're talking about the values for B0 and B1. So that's what we have here. So based on 60 observations, the model automatically calculates the estimated values for B0 and beta 1. Now we have to remember these values were calculated using 60 observations, which is a sample. But whenever you're using a sample, there's bound to be errors. So that's what the second column measures. It says, what are the errors associated with these estimates for B0 and beta 1? Now this third column, which is referred to as t-statistic or t-stat, measures, and it's right here, measures how far the value for B deviates from the hypothesized value when measured in units of standard errors. Basically what we want to know is how far is the B value from the hypothesized value. Now the default assumption for the hypothesized value is 0. So what's going on here? Basically, we want to see if the values for beta, the B's, the coefficients, are significant. In other words, are these values far away enough from 0 in which we could consider them to be significant? And that's what t-stat says. So therefore, this value here is only 0.2857 standard errors away from 0. That's not far at all. However, if you look at the value for B1, so if you plugged in B1 here, and you made this 0, and then divided by standard error, you would actually get this number. And it would tell us that the B1 value, this one here, is 2.667 standard errors away from 0. So you could see that the B1 value is much further away from 0 and therefore more likely to be significant. Now how do we measure the standard error, the slope coefficient? So we're talking about this guy right here, because this one is the most important. B0 is a constant. Let's go to our framework here again, this guy right here. Because look how basic this is. This is our starting position when we're analyzing regression. B1 tells us how sensitive the y is to the independent variable. So the B1 is very, very important because that's capturing the relationship. So how do we quantify it? Specifically, the standard error associated with B1. We take the standard error estimate and we divide it by the square root of the sum of the difference between the xi and the mean of x squared. So it's right there. Now, on the exam, are you going to be asked to calculate this? It's possible, but in my opinion, unlikely. Why? Because I think it is far more important that you know the significance of standard error rather than calculating its actual value. But nevertheless, it's there. And what we can see from this framework is that holding SEE constant as the variance for the independent variable increases, the standard error for B1 will decrease. And where do we get variance increasing? Because if you look at this, when you're sort of calculating the dispersion of individual values of x from its mean, you're actually calculating the variance for x itself. So that's the connection. So when the variance increases, that's like the denominator getting bigger, and therefore this term gets smaller. But if the standard error gets smaller, look at the connection, ladies and gentlemen. So from this, you get this, but then standard error is over there. So standard error decreases, the t-statistic increases, which means the coefficient is even further away from 0, and therefore even more likely to be considered as significant. So here's the regression model. This is the generic framework. So now all we got to do is we got to plug in the estimates we got for B0 and beta 1, and there it is. So this is the whole point of the regression software, is that it does the calculation for us. We just have to input those 60 observations, and then it'll tell us what B0 and beta 1 is. And what we want to do is we want to test the hypothesis that the true or population coefficient is equal to 1. In other words, what we want to see is stock D as sensitive as the mark-in? Because remember what beta equaling to 1 implies. It means that the stock, so if this was 1, if the B1 was 1, it would mean that if the markets went up by 10%, this would go up by 10%. On the other hand, if the markets drop by 10%, then the stock return would drop by 10%. So that's what B1 means. It means that stock D is as sensitive as the market itself. But I don't get it. I thought our regression model gave us a B1 value of 0.8. Yes, but that was based on a sample. So what we want to know is, after you factor in sample errors, is it possible that the true or population beta 1 is equal to 1? So we really have to understand the reasoning behind these hypothesis tests. We're using a sample to draw conclusions on the population, but when you draw a sample, there's going to be errors, and we need to take that into account when we're doing these hypothesis tests. So let's start the process for hypothesis test. We state the null, and here's the null. It's the claim that the beta is equal to 1. And from previous chapters, we know that if there's an equality in the null statement, it results in a two-tailed test, because that means we're willing to accept values equidistant on either side of 1 once we factor in that margin of error. And then, of course, the alternative statement is the complement to the null. So if we disprove the null, then it means that the beta 1 is not equal to 1. Step 2, we look at the level of significance. Now this will be given, so assuming that we're told the level of significance is 0.05, it would indicate that we have to give the null a 95% margin of error. Again, because this test is based on a sample. So I'm willing to give this statement a 95% margin of error to account for sampling error. And then step 3, here's the test itself. And I always use the analogy of a penalty kicks when I'm doing hypothesis test. So here's the null, and here's the goalposts right there. So if the sample or the ball falls anywhere within this range, we would say, you know what, that's null territory, we'll go with the null. But if the ball, i.e. the sample, falls anywhere outside of this range, then we say, you know what, our sample simply does not support the null, and therefore we would go with the alternative. Now, I'm using words like goalposts and ball, but in quantitative analysis terms, for the goalposts, we refer to it as t-critical values. So to find those t-critical values, i.e. the goalposts, we have to specify the degrees of freedom and the single tail area. Now the degrees of freedom in this case would be n minus k plus 1. And k is the number of independent variables in the regression. Now in our illustration, so here's our regression, we only had one independent variable, and that being the market return. And that's why for k, I just plug in 1. So therefore the total degrees of freedom would be 58. And the single tail area, let's see here. So if we know that the 95% acceptance range is in the middle, i.e. centered around the null, then that would leave 0.025 in each tail. So now I'm going to take you to the t-table, and we're going to look for two parameters, the degree of freedom and the single tail area. and see what the table tells us with respect to the T critical. And what T critical is, I know I keep referring to it as a goalpost, but T critical is saying how far do the goalposts have to be away from the null in order to cover that 95% margin of error. And here we are. This is your T distribution, and notice how it asks for the area for one tail. So the two parameters that we're looking for is the degree of freedom, and there it is. I know our degrees of freedom was 58, but the closest one we have is 60. That's okay. And then the single tail area was 0.025. So when we triangulate these two dimensions, i.e. right tail area and the degrees of freedom, we get a critical value of 2.0. And that's exactly what we got here. So again, the interpretation of T critical is we need to go plus and minus 2 standard errors away from the null to cover this 95% acceptance range. So that's your goalpost. Now in my penalty kick analogy, I ask you, where did the ball come in? Did the ball come somewhere in here within the goalpost or outside the goalpost? And that's what T-stat is going to do. T-stat says, how far did the sample deviate from the hypothesis measured in units of standard error? So it's basically saying how far did the ball deviate from the null. So notice how everything is measured from the null. Whether it's the goalposts or whether it's the sample, it's always measured from the null. So let's find that out. The sample value for B1 was 0.8. The hypothesized value was 1.0, and the standard error was 0.3. So therefore, the sample deviated from the null minus 0.67 standard errors away. So again, we start from the null. Now, if this left goalpost is minus 2 standard errors away, but we're told that the sample is only minus 0.67, that means it deviated a smaller distance away from the null. So therefore, the sample would be somewhere there. And then you look up, you say, oh, that's null territory. So then you just go ahead with the null. So the decision rule, since the sample falls within the null range, in other words, the T-stat, which is 0.67, was less than 2.0. And notice we're taking the absolute values here, ladies and gentlemen, because it doesn't matter. It doesn't matter if the sample came on this side or that side. So whether it was minus 0.67 or plus 0.67, it doesn't matter. The important thing is it fell within the null range. So that's why we look at the absolute value. So these negatives don't mean anything. And that's exactly what we got here. Now, of course, I like this approach better because it gives you that visual. You can see the big picture of everything that's happening. But nevertheless, this is the algebraic format of what we saw with that visual framework. And what this means is if the absolute value of the T-stat is less, it means the ball came inside the goalposts, which is null range, and therefore we do not reject the null. So how do you interpret that? Well, if you're not rejecting the null, what you're saying is it's possible that the null is true. In other words, it's possible that the population beta 1 could be equal to 1.0.